Okay, so today what we're going to be doing is we are first going to be reviewing and finishing up the UARt code. All right, the UARt chapter last week we covered all the theory aspects of it. All right, and we stopped at the part where we're going to review the code. All right, so what I'll be doing is I'll be actually going through the lab manual now, so you understand what is happening and you know what to expect. All right, and also what you should do to further the code given to prepare for the project. All right. Okay, so what we will do is we will first look at the lab manual. All right, so let me share the lab manual with you. Okay, so this is the lab manual for this week. Okay, on UART. All right, if you see the objectives, basically you are going to explore the UART capabilities. All right, and we're going to be using the UART2 module. Okay, so what we have here is I've given you the initialization code. All right, so initialization code here has a few different parts to it. Okay, so let's go through section by section and then we understand. So as we are going through, we are actually also trying to understand some of these questions over here. Okay, so let me put it to you through here, the actual code here. All right, so this is the code, all right, to initialize the UART2 module, and then we're going to look into the transmit and receive codes in a while. Okay, so the first thing is what is the baud rate that you're going to operate on. All right, so I've chosen 9600. All right, I believe that is also the default setting for the BT06 module. All right, so it's sort of it's easier. The next is the port. All right, so which port are you going to use? Which pin are you going to use? All right, if you have been looking at the data sheet, okay, so let's bring up the data sheet. Okay. So the port muxing signal multiplexing is in chapter 10. All right, so if you go down to look at the port UART2, okay, you will see that in many cases the same peripheral block may be mapped as alternate functions for different pins. Okay, so for example, okay, you can see here that UART2, okay, let me zoom in here. UART2, okay, is mapped to port E22 and port E23 as transmit and receive pins. And so if I use port E22 and port E23, all right, I will be using them as the alternate for multiplexing option. All right. Okay. So if you scroll down, you may see that the UART2 okay, the UART2 can also be mapped here. All right, so you can see UART2 transmit and receive can also be mapped to port D pin 2 and port D pin 3, or port D pin 4, port D pin 5. All right, so if I want to use these port pins, then I use the alternate 3 option. All right, so you have to be you have to understand that you have a few options. We choose the option based on uh, the pinouts that are available to us. All right, if you want to use other pins and those pins are available, that is also up to you. You just need to make sure that you configure the correct port and you choose the correct alternate multiplexing option. Okay, so in the sample code that I'm showing you, I've been using the port E22 and 23. Okay, so in that so because of that, I'll be using that port and the alternate for function. Okay, so if we look back at the code, all right, so the first thing that we do is this. By now you should know what is this for. Anybody can tell me? What are these two lines for? Okay, so it's to enable the clocking, correct, to the two different modules, peripheral blocks, correct. Okay, so this is by now is a common thing that you'll be doing almost every week, correct? When I want to use a peripheral subsystem, I need to enable the clock to it, and all the clocking, clock gating options are in the SCGC registers. All right, so there are different SCGC registers for different peripherals. You just refer to the datasheet to know which one I should reference and which particular bit. All right, the bit wise is a bit easy because we already have all these masks defined for us in the header files. All right, so you don't need to go and count the exact bit that it is located in, as long as you know which is the correct register you're talking about, okay, in the data sheet, then you know which one to reference. All right, so that is good. Okay, most of you are already familiar with that. And then this is what we just talked about just now, where you enable the multiplexing option, all right, to choose the correct function for that particular pin. Okay, so this number, this pin, this number 4 is specific to that particular port, correct? So like what I showed you just now, if I were to use port D pins, then it would have become mux 3. All right, so in port E2223 is mux 4. All right, because this is the alternate 4 option for that particular pin. All right, so in this 4 lines, that is what we are doing. We are trying to make sure that the multiplexer selection is done correctly, that we are using the UARt module for that particular 2 pins, transmit and receive. Okay, this line here, can you refer to your data sheet, look for the C2 register and tell me what are we doing here? Okay, like I said, your data sheet should always be on standby, all right, because we will refer to it a lot, all right, for all the programming or device driver configuration. Okay, so there are answers coming in. So let's look at the UARt2 C2 register over here. So okay, so the UARt2 C2 register TE and RE. TE and RE is basically to enable and both the transmitter and receiver. And what the code is doing is it is writing a complement of the mask value. So if I go to the mask value, the mask is basically setting that bit to 1. So the complement of that would be 0. All right, that means effectively I am writing a 0 to the TE and RE bit. All right, okay, so most of you have got that. So we are now disabling it. Okay, we're not enabling it. All right, because we are writing the complement. All right, so currently we are clearing both the TE and RE. Okay, why you want to do that is because we are now setting up the module. All right, we do not want a case where accidentally maybe some other code that you written and you or somebody else wrote that accidentally would have enabled this transmit and receive. All right, and you do not want it to be enabled while you are setting it up. All right, so it's always a good habit to make sure you disable it first, set it up, and then you enable it. All right, so it's a good habit. Why I say that is because in general, when you work in group projects, all right, someone else's code may interfere with your code, all right, because they may have made some assumptions and accidentally written to some registers that you are also going to write to. All right, so it's always good to do it in the proper sequence for your own particular module you're working on. All right, now this part here is okay. So let me explain this one first. So the first thing is bus clock and system clock. So what is the default system clock? So for me, in this case, I am clocking it at 48 megahertz. All right, so I've up my system clock over here. And what is the bus clock? Okay, so in our this KL25Z microcontroller, there are 2 clocks. One is the system clock, okay, which clocks the CPU, and then you have a bus clock which you apply to some of the peripheral subsystems. All right, and the UARt is one of those subsystems that runs at half the system clock rate. So if I run my main clock at 48 megahertz, my bus clock will run at 24 megahertz. All right. So this is basically how it is designed internally. So when you are calculating the values for the baud rate register, you need to first divide the system clock by 2 and then use the bus clock. All right. So this is it's just the way the system is designed. Correct. They have two separate clocks. Okay, one for CPU core, the other for some of the subsystems. All right. This so when you want to find the divider, so basically you are going to transmit or receive at a particular baud rate. The baud rate is basically the bus clock divided by the baud rate will give you the divider, correct? So what is the scale I want to divide by? But in the denominator, that you see a times 16. Can anybody remember why we have to do this times 16? Correct. Okay, so good. Some of you remember of the oversampling. All right, so the UARt module internally does oversampling of the data. All right, the reason is to help to minimize error due to any noise or interference in the signal. So oversampling, and then you take the max mode kind of a response, gives you a higher chance of getting it correct. All right, so this divide by 60 is something you don't see, or you may not see in other calculations or in other controllers. All right, so this is unique to this controller because of the oversampling. Okay. Okay, what if there is a tie? All right, so if there's a tie, it may interpret either way. So it may flag off as an error if you have enabled parity checking or something like that. Correct? Or in the event there is a tie, it may set one of its own error bits. All right, so in the UART module, if you look at it, there are a few error bits there. All right, so it may trigger one of those error bits to tell you that there is error in the data due to noise. All right. Then the last part is getting the, so this divisor value you then need to write to the two registers. Okay, so these two registers are divided into baud rate high register and baud rate low register. So that is what you're doing over here. Okay. Okay, so this tree C1, S2, C3. Okay, all three I set to 0. Okay, can you all go and have a look at C1, S2, and C3 and see why we set it to 0? Or do we need to set it to something else? Okay, so look at the C1 register, look at S2 register and the C3 register. Okay, so let me look at the C1 register first. So if you look at the C1 register, there are a lot of other features here which we are not using. For example, 9-bit transmission. All right, if you want to transmit 9 bits at a time or receive 9 bits at a time, then you can enable this n bit, okay, which you're not using. All right, this idle line type select, all these are additional very minute configuration that you can change the behavior, but we are not doing any of that because we want to keep the behavior as default, okay, how the normal serial interface behaves like. The only thing that probably you may want to change if you are interested in is the parity. All right, so if you want to add parity to your transmission, okay, then you need to make sure you enable parity and whether you are doing odd or even parity. All right, so in my example, I'm not doing parity check, so everything is 0. All right, so that is your which register was this? This was your C1 register. All right, the next one is your S2 and C3. Okay, so let me jump to C3. Okay, parity is not 9-bit. Okay, 9-bit data is the additional 9th bit that you want to send as part of your data packet. All right, parity, when you enable parity and you set odd or even, the additional parity bit is automatically generated by the hardware. Okay, so if your data transmission is involving 9 bits, then you enable 9 bits. If it is 8 bits plus parity, you just enable parity and the hardware will do it for you. Okay, so let me go to C3. Okay, the other one was S2. So this is S2 register. So if you look at S2 register, again, you have a lot of other configurations here, like receive data inversion. All right, that means you want to reverse the polarity of your data. Okay, you want to detect a break in the line. Okay, things like that. So these are all a lot of very additional configurations which we are not going into those details right now. All right, so we don't need to configure any of these bits. Okay, and the last one is the C3 register. All right, so the C3 register here is uh, if you are dealing with 9th bit data, all right, because your actual data you transmit, you write to a particular register which is taking in 8 bits at a time. All right, so the additional 9th bit you need to write into this register here. All right, so if I want to transmit 9 bits of data, then 8 bits go into the data register and the 9th bit will be added to this particular register. All right, the hardware will take care of taking this 1 bit from here and adding it to the 8-bit data and then sending it out. Okay, the other one is things like interrupt enable for error. Okay, so as you can see, there is a noise error interrupt. All right, so this is what I mentioned just now. All right, so if you look at these 4 errors: overrun error, noise error, framing error, and parity error. So these are the different type of errors that the hardware can detect for you. If you want to be able to detect error and handle this kind of error cases, then you can enable interrupts. All right, and then use interrupts to go and figure out what went wrong. Okay, so again, in my case, I'm not going to handle interrupt. Do you need to handle interrupt for handle error for your project? Not necessary. Okay, why? Because in your case, uh, if you press a button and the robot doesn't move, what will you do? You probably press the button again. Correct. And if it still doesn't move, then something else is wrong. All right, so you're not going to set up unless your intention is to set up a very complex two-way communication, where if there's an error you want to send back to your app. All right, but even if you send back to the app, okay, there's nothing much you can do if there's an error on the receiver side. Correct. At most, you will send the data packet again. All right, so in our case, there is no necessity to do any particular error detection or correction. As long as you're able to transmit and you can receive and decode the data, then it should be fine. All right, so after all the configuration is done, then I come back to the 2 bits just now, and this time around I do a OR. So previously, what did I do? I do an AND with the complement to clear the transmit and receive. In this case, I do an OR with the TA and RE enable. So this is where I actually turn on the transmit and receive. Alright, so at this point of time, the transmit and receive is already on. Okay, it's running. Okay, so in my main code over here, basically what I do is I initialize the UARt, and in my case, I just transmit, okay, this particular bit 0x69. Okay, and then I just delay for a while and then I transmit again. Okay, so let's look at the transmit function over here. So in the transmit function is basically checking. I have this loop here while I'm checking for this condition while not this. So can you all check and tell me what I'm doing here? Why am I checking this particular bit in this register? Okay, yes, all right. So we are okay. So the comments are coming in. So it's checking whether it's empty. All right. Okay. So the TDRE register is transmit data register empty. So we are trying to check whether it's empty. Okay. So while it is not empty, I just wait here. All right. So I'm stuck in this loop as long as it is not empty. All right. That means there is some data that is being shifted out at the moment. All right. Once the transmit data register empty flag is set, means that the register is empty. I can now put a new data inside to transmit. So that is what I'm doing here. Alright, so you can see it's a fairly simple code. I think it's a bit similar to what you did in your Arduino Uno as well. Correct? You try to check whether the register is empty, and once it's empty, then you put in a new data and then it gets shifted out. Alright. For the receiver side, okay, so we're not doing receiver here in the example, but in the receiver side, you have something similar. Alright, you just check for the receive data register flag. Alright, and while it is not empty, okay, then you can read the data out. Okay, so it is quite similar to, I think, your Arduino Uno, the way you did the code there as well. All right, so basically if you look at this S1 TDRE, you can see the data sheet, you will see the explanations there. So basically this is what the code is. All right, it's a simple code to set up your UARt and transmit this. All right, now so let me show you what you expect when you run the code. All right, so the first thing is your transmit and receive pins. So I'm using port E22 right now to transmit. So if you look in your layout, okay, port E22 is okay, facing up on the left hand side, the top right corner, this particular pin. Okay, so please make sure you are monitoring the correct pin, and of course you need to have a reference ground, right? So any of the ground pins you can use as a reference for your oscilloscope. Okay, so the waveform you will get is going to look something like this. Okay, so let me zoom in a bit. Yeah. Okay, so if you look at the waveform, all right, this is basically what is being transmitted out right now. All right, so this is the okay, so this is the idle line. All right, so before I transmit anything, it is idle, it is high. All right, and once I start transmitting, okay, the first okay, so the first bit is your which bit? This low is which one? Okay, yes, correct. The low is the start bit. Okay, so if you look back at your UARt documentation, all right, in the slides, you will see that the idle line is high, and when a transmitter wants to transmit, it will pull the line low. All right, so that is the indicator of the start bit. So the receiver also knows that suddenly somebody pulled the line low means somebody is going to start transmitting data. Correct. So the moment one of the devices pulls the line low, that informs the receiver that it's time to prepare and sample data in. Correct. So this is the start bit. So after the start bit, you have a few bits of information. So you have 1, 0, 0, 1, 0, 1, 1, 0. Correct. So this relates to what? So 1, 0, 0, 1 is 1001 is 9, correct? And then 0110 is 6. All right, so you can see that you transmit out as the least significant bit first. Okay, the least significant bit goes out first and then followed by the most significant bit. And once you finish, so if you look at the right side, once I finish, I pull the line high. That is the stop bit. So the transmitter will pull the line high to indicate that it is stopping this current data packet transmission. Okay, so this is basically what you will observe, all right, when you probe your transmit line. And if you can see over here, if I zoom in a bit more, the frequency. Okay, so the frequency you cannot do any auto measurement because it is random bits. So what you can do is you can place the cursors over here. Okay, and with the cursor placement, okay, for the bit over here, you can see that the time difference roughly comes up to 9,600 okay bps. All right, so this is what you would observe in the lab. Okay, so the next step is of course for you to extend this, all right, and then integrate the Bluetooth module together with the receiver. All right, so that part is where you need to look back at the video that I've sent on the connections between the 7805 regulator, the BT06, okay, and then to your freedom board over here. All right, so the reason why we need the 7805 is your BT06 requires at least 3.6 volts and above to work. Okay, 3.6 to 6 volt. Your board here only has 3.3 volts. All right, so it's not enough to power the BT06. All right, so that's why we are using the 7805. Okay, so how you want to design the battery sort of configuration is up to you. You have 9 volt supply. You have another AA battery pack. All right, that you have. So you can decide how you want to do it. Correct. In the past, some students use the 9 volt to power the 7805 and then use that for the Bluetooth part. All right, as well as to power the freedom board. All right, and then the AA battery pack, they use it for the motor driver power. All right, so that seems to have worked well so far. All right, but if you want to try out different power system configurations, also up to you. Okay, so that is basically for this week's lab. All right, so that you know what to do. And like I said, don't stop at just doing the lab manual. You should try to build up on the Bluetooth side, okay, and the app side as well, so that you have the full sort of interface working. All right, once you have the app that can communicate through Bluetooth to the freedom board, that solves a big hurdle already. All right, because you have completed PWM last week, which means you can control the motors, and this week you can complete UARt means and the Bluetooth everything. Then the whole framework is set up already. All right, the only thing left is putting all these subsystems together into the RTOS architecture. All right, so try to settle everything soon, okay, in terms of this low level stuff, so that when you build up the architecture, you can just integrate all these device drivers inside correctly. All right, and then everything will just work. All right, so the one thing that is not shown here, which is also something you need to do, is extending this to use interrupts. All right, so over here, okay, so this is the part I mentioned. So two things: UARt over Bluetooth, all right, which you need to try, all right, and then you need to convert this to interrupts. So this is a requirement, all right. If you look at the project document specifications, the UARt must operate on interrupts. All right, so you need to make sure that is done. So for the interrupt part, okay, I've given some handouts in the lecture slides itself. The important thing to note is you want to make sure the UART IRQ handler is a unified handler for all the interrupts related to UART. That means transmit interrupt, receive interrupt, error interrupt, all of them that are tied to UART2 would all come to the same UART2 IRQ handler. Okay, so that's why I've given you some sample code in the slides to make sure that when the interrupt happens, you check why is the interrupt happening. But in our case, it's quite straightforward in a sense, because the only device or the only event that will trigger the interrupt is because you are receiving something. All right, like I said, you're not transmitting anything from the freedom board back to the app. So the only interrupt that you actually need is your receive interrupt. All right, so as long as you are able to monitor the receive interrupt, and then based on that you take some appropriate action, then you can sort of convert the polling to interrupt quite easily. All right, so you can refer back to some of these sample code in the slides that I have. All right, so that basically wraps up all the hardware elements that we needed to cover, all right, in terms of the freedom board and the microcontroller, so that you can build up everything. All right, so now what we're going to do is we're going to move on to RTOS. Okay, so let's start off. So today we're going to do things a bit differently. What I'm going to be doing is we are going to cover this. So lecture slides 9 and 10 are fairly small set of lecture slides. So we'll cover those slides, and then we will have sort of a group tutorial session for the tutorial on the OS introduction. All right. The reason why I want to do it is because it's quite important that we understand, or that all of us have the same understanding of the basic concepts of OS. All right. So that's why I want to run this tutorial with all of you. Okay. So let's start off with the lecture 9 first. Okay, so this is a brief overview on OS, correct? Okay, so now that we are transitioning, okay, from a single threaded environment to a OS based environment, what we need to look at is exactly how the OS is actually going to help us in a lot of different areas. Okay, so when you have an OS, you need to look into things like how will you manage multiple processors, how will it manage memory, all right? And in a system, all right, definitely, I mean, not all embedded systems, but in more complex systems, you have things like file storage, right? So if you talk about being able to play music, playing video, and so on, so there's a lot of files you need to store. So how do I manage these file systems? All right, input output. Besides GPIO, which is what you're dealing with, anything related to any user interface, right? A touch screen, a Bluetooth module, okay, a Wi-Fi interface. All these are part of your input output sort of configurations. Network and security are also other areas where the OS will come in, and of course the GUI. Okay, so what is the whole idea of a process? All right, so the operating system itself provides you with the backbone, all right, to run a process. All right, so what is a process? A process is basically, you can say it is the user application or system application that is doing some activity related to either maintaining the OS or providing some feature for the user. All right, so if you talk about a handphone, for example, you may have processes that will run in the background to maintain the integrity of the system, all right, that is running properly and well. At the same time, you have user level processes, right, the apps that you run that will also be running in parallel with your system processes. All right, in most cases, the process, we abstract it as much as we can so that the background OS takes care of a lot of the low level and backend stuff for us. It is also possible that you have multiple processors running the same program at the same time. Okay, just like how you can open up Microsoft Word, a few different documents at the same time, correct? Though you have only one Microsoft Office application installed, correct? So each time you open up, it's a new instance, a new process, all right, of the same application, all right? And at the same time, each of document you can edit concurrently, correct? So because they are all occupying separate memory spaces, all right? And just because you close one document doesn't mean everything closes, correct? So everything is separate in its own space, okay? So because of that, you also need to take into account the creation and destruction. So when I create an app, when I create the process for a particular program, what are the steps I need to take, okay? And when I decide to end the process or terminate the process, what must I do to do a proper cleanup, okay? And things like scheduling, communication, and concurrency. Okay, so scheduling, communication, and concurrency, these are things that currently we do not think so much of when we use a desktop system, correct, or use your handphone, right? In a sense, because we take the behavior of the application to be how it is, correct? So if I say that, for example, you open up an app on your handphone and it's slow, okay, it starts to lag, it's not so responsive, all right? Intuitively, most of us will blame it on the app itself, all right, that is not well written, all right, so that is why it's buggy or things like that. But the issue could also be at the back end, all right? That means the way the OS is handling the requirements of the app is not optimal, all right? So that is why it is causing a lot of issues with scheduling the requirements of this app or providing the necessary communication framework, okay? Maybe the app needs to communicate over Wi-Fi or over Bluetooth, all right? And something is holding it up. So a lot of things at the back end or the OS level could also impact on how a process is actually executing. Okay, so in terms of memory, all right, we need to look at things like how programs stored in the memory, okay? When you talk about programs, you also talk about the data as well, all right? Then, of course, how do you share data between processes, Right? So you may have a common data structure, right, where you have process 1 and process 2, and both may require read-write access. And this kind of situations can lead to a lot of data corruption if it is not handled correctly. Right? So how do you handle this kind of things? All right, so there are things that you need to look at, and pages, virtual memory are things that you can do to improve the performance of your system. All right, so we will be looking at virtual memory towards the end, okay, of the module. Okay, file and IO, as we know, file is basically another abstraction towards storing large amounts of information. In most small scale embedded systems, you may not need a file system. All right, in some cases, just a basic directory structure might be enough, correct? If you just want to keep logs of certain activity. Okay, but in some embedded systems, like I say, you have a MP3 player or you have a GPS or something like that, you may need a more well-tuned file system because of the amount of data you're dealing with. Okay, IO is basically a lot of things that we have been dealing with, okay, the past few weeks. So we need to make sure that we know very detailed information on how the device works, like what we've been doing, understanding how the Freedom microcontroller works, and we need to make sure we have the appropriate device drivers to talk to all these IO devices, okay, in the system. Okay, so in the operating system structure, it is not so straightforward. Okay, why? Because you need to rethink your whole thought process. All right, in a sense, you are now trying to break up the old model of thinking where you have a linear structure and then you have interrupts, and now you are saying that you want to break it up into a more modular system where every module behaves independently. Correct. So it is a challenging sort of task, correct, because you need to think of a few different things. Firstly, it must be reliable. Okay, it must be backwards compatible, because this is in a sense where you move forward in the program, and then you still want to be able to support older subsystems or older modules or older hardware that you have used in the project. Okay, the other thing is extensibility and portability. So this is also important because the whole idea of moving to OS is you want to make the system be future-proof to some extent. That means I must be able to grow my system, provide more features, more capabilities, okay, while keeping the current framework. Right, so that is one of the biggest advantages of using OS. In terms of a RTOS, okay, so OS and RTOS, what's the difference? Okay, so the main difference, okay, of course, in terms of word, we have this real time, right? So what is this real time? The whole idea of real time is to be able to meet specific timing constraint. Your general purpose OS like your Windows or Mac, okay, or even your handphones, they are not RTOS, they are not classified as RTOS systems because they do not have specific timing constraints to meet. All right. I mean, as a manufacturer, as a developer who is designing the OS or the system, they may have their own benchmarks, correct? But as far as the user is concerned, okay, if today I click on my Google Chrome icon, it takes 200 milliseconds to launch. If tomorrow I click, it may take 500 milliseconds to launch. It is still fine for everybody, correct? So we do not say that just because it took 300 milliseconds longer, something is wrong. No. We accept that there will always be some delay or difference in the timing performance every time you open up the laptop. All right. Whereas a real-time system cannot afford this luxury. All right. If I say I press this button and this event must happen, correct? So within 2 milliseconds, it must happen. Correct. So this is of course very, very critical because it's a matter of life and death in cases where you design systems for healthcare, for medical applications, or even transport. Correct. So for example, you're designing a ABS system or a airbag crash support system. Correct. The moment the crash is detected, within a few microseconds, the sensor must trigger and blow the airbag. Correct. you cannot have a system where the crash is detected and then you have an OS that says, oh sorry, I'm changing the song in the MP3. Can you wait for a while? By the time the fella is gone, or I cannot hear the music anymore. All right, so you need to have this kind of hard timing constraints for real-time systems where there is no leeway. Correct? You cannot play around with it. All right, so that is again the most important thing of a RTOS system. Right, the predictability and determinism. Okay, you must be predictable. All right, and of course, this is something I asked, I think, in a poll a few weeks back. Is real time equals to fastest response? Okay, so the answer is no. Correct, because like I said, the response must be within the deadline. Okay, it's not necessary that it has to be the fastest as long as it meets the deadline. If my deadline is 1 second, if it happens within 100 milliseconds, 200 milliseconds, or 900 milliseconds, it's fine. Right, as long as I meet the deadline, that is good enough. Right, so that is the main thing of RTOS. Okay, sometimes you will read some articles or books where they talk about embedded operating systems. Embedded operating systems are, in essence, very is a term loosely used together with RTOS. So in a sense, they are interchangeable, right? Because there is no clear distinction. And the reason why we sort of use them interchangeably is because when you talk about an embedded OS, in most cases you have an OS in an embedded device because you will have real-time requirements to fulfill. Okay, if you have an embedded device that has no particular real-time requirement. Okay, so for example, you create a remote control. All right, so there is no particular real-time demand. Okay, so even if the TV changes channel 1 millisecond later, a few milliseconds later, doesn't matter. All right, so in those cases, that's why we interchangeably use embedded OS and real-time OS. All right. Okay, so again, all of these factors are, as what I said before, it must be predictable, it must be real time, it must be fast enough. All right, and in terms of embedded OS, other factors may or may not be important. Okay, so some may have a GUI, some may not have, some may need security, some may not. All right, so it all depends on the application. All right, so the whole idea is we want to move away from the super loop approach to the RTOS on the embedded system. All right, and the main idea is you want to create a system that is scalable. Okay, so this is important. Now, if you just think back at your EPP2, for example, okay, so you have a system, all right, you have your wheels, okay, so you have a LiDAR there, correct? And so this is the basic structure of the system, all right? Now, imagine that you work on your traditional approach, which was to have the whole loop with your interrupts and all this thing, correct? And everything works fine, right? And then along the way, there's a change, correct? And we say, oh, we need to add one camera module in front, okay? Then we say fine, okay. Then where? So in your code, you have a super loop, correct? You have a while one loop, all right, and then you have a lot of activities, task 1, task 2, task 3, everything. So now that I add this camera module inside, where do I insert this? Correct? Because wherever I insert, there is now going to be some impact to the overall timing of the super loop. Correct? So the overall characteristics will change. Now, of course, you can use interrupts as much as you can, but there's also a limit to how many interrupts you have and how much tasks you can do in your interrupt. Correct? Then it extends some more. Correct? So imagine that now I have a blue camera, and then I say this camera data must then be transmitted through Bluetooth to a laptop. Correct? So you have another activity that needs to now run in. So this Bluetooth must also run together while I'm capturing data. So where do I insert that now? Correct? And then if let's say now I add another sensor at the back, another 2 more IR sensor at the back. So where do I add this? So you can see that when your requirements keep changing or keep scaling, all right, the traditional way of thinking will add more and more uncertainty, all right, because you can make it work, okay, you can make it work, but you need to then fine tune a lot of things, correct? Because every time you make a change, the timing characteristics will be affected. So you need to go and re-examine and then try to see where do I make changes to still fulfill the timing requirements of the system. All right. So this method of thinking we are now going to change. Correct. So instead of changing, instead of doing it this way, we are now going to change the entire thing and say, okay, now I say that LiDAR is one task by itself. Okay, my motor control is one task by itself. Okay, my sensor is one task by itself. Okay, my camera is another task by itself. So everything is one task. All right, so the LiDAR's job is to capture LiDAR data. Motor's task is to move motor. This is to capture sensor and this is to capture camera. So every component, every subsystem, I can now treat it as an individual entity, focus on something. Correct? And then what else must we think? We must now think, how will all these different modules or subsystems now talk to each other? Correct? So there will be a lot of interaction. Correct? The LiDAR information must be sent back to some main routine that will decide what to do with the motors. Correct? And the sensor information will also need to be updated to decide whether to stop the motor or to move the motor. Correct? The camera data must be sent to the Bluetooth module to send over the network and so on. So I will then need to rethink how will all these subsystems talk to each other, how will they communicate. Correct? And of course, another important thing is priority. Who is more important? Correct? Which task is more important, which task is less important. So all this will now affect the dynamics of how a system behaves. Okay, so when you first transition from this super loop over to this multi-threaded environment, it will be a huge change, right? A huge change because you need to rethink a lot of aspects of your design. But once your multi-threaded system is, the structure and the architecture is done properly, you will find that it's very, very easy to scale. Correct? If tomorrow suddenly you say, I don't want the camera anymore, I want to take out the camera, no problem. Correct? It's very easy to detach the camera and you just need to make very small changes to the rest of the code. Alright, and the system will still run because everything you have established a relationship, okay, on how one module interacts with the other module. Okay, so you will find that it's very easy. Right? And if tomorrow you decide that instead of one motor, you want two motors, or instead of two motors, you want four motors, it's very easy to extend. Okay, so it's very easy to scale the system once you have it in a proper architecture. Okay, so for this course, all right, we are going to be looking at the KL RTX. All right, so this is the RTX RTOS that we are going to be using. All right, it has a well-established support, okay, for the Cortex-M cores. All right, and it's a well-rounded RTOS. All right, in terms of the code-wise, there is also another application layer called the CMSIS RTOS API. So in our code, you will find a mix of the KL RTX as well as the CMSIS library functions. Okay, both of them will help us to access many of the OS-related calls that we will be seeing. Okay, so that is basically to give you a good overview. Okay, so we will take a short break now. Okay, now it's 9:53. Okay, so we'll come back at 10 o'clock. Okay, and then we will go through the next set of slides. All right, and then we will have some discussion on the tutorial question. All right, so I've also sent out the next tutorial. Okay, just before the class started. So go and download that and keep it as well. All right, so once we go to the next set of slides, we will have a discussion on those questions. Okay, so I'll see you all back here at 10 o'clock. Okay, so let's come back and carry on with the next set of slides. So in this next set of slides, all right, basically we are going to get introduced to the idea of processors or threads, all right, and see how they will actually be used, okay, to run the overall architecture. All right, so just now in the chat there are some questions about is it single thread or multi-thread or what. So how are we breaking up the modules? So just now in the example when we say I break up this idea into a module for LiDAR, a module for motor, a module for sensor and so on, what I'm referring to is each of these will run its own thread, its own process. All right, so that means there'll be a process or a thread created to perform the LiDAR interface. There'll be one for the motor interface, there'll be one for the camera interface, and so on. And then in your overall architecture, you will come up with a framework. How will these different modules talk to each other? How will they synchronize? How will they share data with each other, and so on? All right, so the whole idea is with the OS, you break up a very big sort of problem into many small modules, all right, which with each module trying to run independently, all right. And the main thing about OS is when you create a process or a thread, you write it in a way that it will run forever and it has full access to the CPU. All right, so in an OS, every process will behave as if it owns the CPU. But in reality, we know that's not the case. All right, in reality, we have one process, one CPU trying to manage all these different processes. All right, so that is where the OS comes in. So the OS manages this for us. All right, so that is what we're going to be looking at now. Okay. Okay, so let's come to this chapter on processes. So we're going to look at what is a process, some introduction to the memory aspect, how do we switch between processes, and then we look at some RTX examples. All right. All right, so what is a process? A process is basically an instance of a running program. Okay, so like what I mentioned just now, all right, you can have the same application like your Microvision 4 or your MS Word or something. You can open multiple versions of it, correct? Each of them doing something different, correct? And each of them has its own memory or private working space. And when I close one, it does not affect the other, correct? That means each of them are running independently with a single instance of a program. All right, so that is the whole idea. That means in this case we have processes that are distinct. All right, in a embedded system concept, you can create multiple processes that are distinct from each other, and yet they are also we are going to explore the framework of them talking to each other. But how will they communicate with each other? In this case, for example, if I open 3 Microsoft Word documents, each of them are separate. All right, but within that process, there is no, within 3 separate processes, there is no communication. All right, so that is something that we will look at in our RTX RTOS, how we can establish communication between different threads. Okay, so what is a process? When you create a process, you are actually creating like a own separate program running by itself. All right, so the process will have a CPU time allocation. All right, that means the OS responsibility is to ensure that I allocate some time for the process to run. It must have some memory because it needs to run the application. Then it will also have some other things like process ID and threads. Okay, so process ID is basically the ID associated with the process. Okay, once the OS starts it up, it gives it a process ID, and a process may also have several threads within it. All right, so the important thing is the operating system, all right, that you're running on is to create this illusion that the process has all that it needs to be executed. Okay, like now when you open up an application on your desktop, okay, you can open up Microsoft Word, you can open up Microsoft PowerPoint, you can open up your Google Chrome. Each of them run separately, and as far as each process is concerned, it is running, it is using the CPU, it's using the system resources, and it is not, in a sense, bothered about what else the CPU is doing. Correct? It feels as if the CPU is dedicated to my application. Right? So even though you are multitasking, each process behaves or thinks as if the CPU is fully servicing itself alone. Correct? Okay, so that is the whole idea of the OS. The OS is to make sure that each process is able to run and make use of the system resources and run independently without being affected by what other applications are doing. Correct? So each process sees one dedicated processor, even though the processor is shared, right? It sees one dedicated processor. It is also sees one portion of the memory. All right. So again, these are all shared, but in the process view, it appears as if it is dedicated, it appears as if it has all the memory it needs. Right? And you can also establish what we call the IPC, that means the inter-process communication between different processes. Okay, so memory layout. Okay, so there will be another chapter where we go into this in more in depth. Okay, but just quick glance of how memory is laid out. Okay, when you compile a program, all right, there are different parts to it. One is of course the code, okay, or the text, which is the binary executable, okay, that you compile it to. So that definitely needs some memory space to be stored, all right. And this is where your program counter actually points to, correct, to fetch the next instruction while it is executing. Then at the same time you have data. So data, you have initialized and uninitialized data. So that also occupies some memory. Then you have static data as well, all right. So that occupies some aspect of the memory. Then in terms of dynamic allocation, you have stack and heap. All right, so stack is when you are jumping to a routine, you jump to the interrupt service routine, you need to save the context and so on. Heap is for malloc and for free. Okay, so these are some general ideas first. We are going to go a bit more in depth into memory aspect in another chapter, right? But this is just to give you an overview of the aspect of what actually a program needs. So as far as the process is concerned, you are switching, all right, between multiple processes, all right, while all this is being managed by the OS. So like I said, as far as we are concerned, we have a single processor and we have a single memory and we have multiple processors, correct? So we have a single, for example, CPU, and you have a single memory. So you think of it as a single entity each, correct? And then you have an OS, all right, that is now trying to manage all these processes. So you have process 1, process 2, all the way to process N. And all of them are talking to the OS. Right? So as far as they are concerned, when they deal with the OS, they feel as if they own the CPU, they have all the memory they need, correct? But the OS is actually trying to multitask all these processes to give each process sufficient CPU time, sufficient memory. Right? So that's the job of the OS. And since the OS is continuously switching, correct, between these various processes in place, it needs to keep track, correct? It needs to keep track of what is happening in each process. So that is what we call the context or the execution context. So this gives the OS the idea of this process, what was it doing? This process, where did it last stop, correct? So things like that. So that means I need to keep track of this memory, what exactly was the CPU, what was the OS doing at that time, and so on. All right, so these are the contexts that you need to continuously save and restore whenever you're switching between tasks. All right, so it's just like, for example, you're working on your report, all right, in one module, at the same time you're doing a presentation, preparing a presentation for another module, correct? So when you continuously switch between the two, you yourself know what you're supposed to type in the document and what you're supposed to put in the presentation, correct? Okay, why you do that? Because in your mind you have a context, correct? That this report is for this module, this is what I need to type. This presentation is for another module, this is what I need to type. So it's the same thing the OS is doing. So it needs to keep a record of what was I doing in this process, what was I doing in this process. So when I go back to that process, I know where to carry on. All right. So so another thing that we will also come across is some OS, okay, we use the term task and process interchangeably. If you look at it from the pure theoretical aspect, generally most OS textbooks, they will refer it as process being created, okay, by the application, and within a process you have multiple tasks. Okay, so you can have task 1, task 2, task 3, okay, which they can communicate and so on. Okay, so to give you an example, for example, let's say you want to watch a video, correct? So when you click on your MP4 file in your system, so that video itself, so you use, for example, Windows Media Player, correct? And you click on it. So that Windows Media Player will start off as a process, correct? But in the code, okay, the source code of the Windows Media Player process, that application may create a few threads. and each thread may be dedicated to doing certain things. So maybe I can say one thread dedicated for the video part, one thread dedicated for the audio part, and one thread for the user interface. All right, and maybe another one thread for the memory interface. Okay, so within the process application, all right, it may spawn a few different threads which can then talk to each other. Okay, so sometimes we say threads, sometimes we say tasks. So these tasks can interchangeably sort of talk to each other, share data with each other, and so on. And these tasks' objective is to make sure that the process can run according to its requirements. All right, so one task takes from the memory, splits it into video feed, audio feed, and so on. And then another task monitors the user interface, interactions, and so on. All right, and all of them work together within that process space. All right, so that is the general concept you will probably read if you look at most reference books or textbooks. All right, but in our embedded system context, all right, we sort of use the term task and process a bit interchangeably. All right, so we refer to them as multitasking or multi-threaded applications, where each task is dedicated to a particular objective. We do not say multiple process because the process in our sense is already the objective of the embedded system. All right, so in our case, why we treat it that way is because when you design an embedded system, in most cases, you have already designed or fixed a particular application need for it. Correct. So if I design a GPS system, that itself is a process, correct? But that GPS system will be running based on multiple tasks, correct? One for GPS data, one for user interface, one for my wireless interface, and so on. All right, so there can be a lot of different tasks within that application context. So that is why most books or references, when you talk about RTOS embedded system, they will generally use the term task or thread a bit interchangeably with process. Okay, but the whole idea is the same. The idea is sort of the same. So that's why I said the reason why I put both of them here is so that if you refer to other material, you do not get confused. All right. So in our context, we take it that process and tasks are interchangeable. All right. But the theoretical sense is process is the higher level hierarchy and task is the lower level hierarchy. But in a sense, all are the same because they all are sharing the CPU and sharing the resources. So what we are interested in how to design this overall framework that can share all the CPU resources and still fulfill the requirements of the system. Okay, so in terms of just now what we said, the execution context, this execution context, so this execution context is actually saved inside this process or task control block. Okay, so each task or each process that you create, you will actually create, the OS will actually create a control block together with this task, and inside this control block, we have all this information. Okay, what is the process ID? What is the state? Okay, what are all the register information? All these things. Okay, so we will cover all this along the way. Correct. And what we need to know is all these are the things that the OS is doing so that it knows what exactly to do when it is switching between the various tasks or the processes. All right, so this is an example of how a task control block looks like. Okay, so as you can see, there's a lot of information. Okay, for now, what we'll be looking at in recent over the next few weeks is things like task state, priority, and the task ID. Right, so these are some of the things that we'll be looking at quite regularly, though you have a lot of other things as well, which we will look at, okay, in subsequent classes. All right, so how do I create a process? All right, so when there is a API call where you need to tell the OS that you want to create a new process or a new task. All right, and once you create a new task, you will actually be assigned a unique ID. All right, so this is the job of the OS. So OS will assign you a new ID. At the same time, it will allocate memory for the control block and all the structures needed to run this process in the proper way for you. Correct? And then you will do some initialization, all right, of the control block and some memory management stuff. So these are things that happen in the background. For us, from the application perspective, we need to know what function to call, how to call it correctly, all right, and then the rest of this stuff is handled in the background by the OS. Now, process termination. That means I do not want this process anymore in the system. This usually does not happen in OS, embedded OS, correct? Why? Because in most cases, like I said, the whole idea is the process itself is the main aim of the application. So any task that you create is supposed to serve some function, correct? If the task terminates, then it could be that something really went wrong, correct? In embedded OS concept, usually, though it is possible to terminate a task, if you intend to do something only once, all right, you will not create a task for it. You can just write it as a normal function call, a module or something, and just call it. Okay, the whole idea of creating tasks is you want to be able to do something either periodically or whenever some event happens, correct? So taking those scenarios into account, you create tasks for that. Right? If it's just a one-off thing, okay, like maybe when the system first boot up, you want to play some melody, you want to play some tune, and it's just a one-off thing. Right? You don't need to create a task just for that. You can just create a function, and some startup task can call a function, and then that's it. Correct? So the idea of termination is more for general OS. Okay, like for example, in your Windows or your app. All right, so you can close the app. Okay, you can close your Microsoft Word and so on. So when you close that, okay, or you close the app, what must you do? You must make sure that you handle the termination correctly. And one of the most important thing is to release the resources and reclaim memory. Okay, because as you saw just now, when I create the process, I'm allocating memory. So the OS is allocating memory for this process to run properly in the system. So when I kill the process or terminate the process, I must make sure the OS is able to reclaim this memory. Correct? If not, that memory may be lost forever, correct? Until you maybe reboot the system or something. Okay. Now, between the different processes, like what we were talking about just now, there will always be a lot of switching that's going on. All right. As far as the OS is concerned, okay, or as far as the process is concerned, each process behaves as if it owns the CPU. Okay, so each process behaves as if it owns the CPU, but the OS is continuously switching between these various processes. Right, it's happening very fast. All right, but at the same time, because of the way it is structured, it is able to fulfill the timing requirements. All right, so since it is continuously switching between the various processes, whenever it switches and switches back, it needs to know where it left off and how to carry on. So that is the context. All right, so those contexts are saved inside the process control block. So that is why the process control block is created the moment you start up a new task. Alright, so the moment you start up a new task, the process control block is created and all the information related to that particular process is saved in the control block whenever you need to do a context switch. Alright, and of course context switching also consumes some time. Alright, but in most cases, the OS and the hardware does everything, alright, in the background, alright, and they are optimized to handle this kind of context switching, right, to make sure that the real-time requirements are fulfilled. Okay, now comes to an important thing, the process state. So when you say we create a process, okay, so different process states, each process can have different states at different time, okay, depending on what is currently happening in the system. Okay, so this is the state transition. Okay, so you can see that the first one is new. When I first create a task, okay, it is new. So that is when I first create a task. When I create a task, it gets admitted into the system. Okay, that means the OS now sees this task. All right. Now, when the OS starts to see this task, okay, and if you have the very first time you have created it, by default, okay, it will always go into this state called ready state. Okay, so what is ready state? So what is ready state? Ready state means it can be loaded by the OS. That means, okay, when I say a task is ready, that means I have all the resources I need to start executing. Okay, so that is what ready means. I have everything I need to start executing. All right, but as we saw earlier, there are multiple tasks or multiple processes that can be in the ready queue. So actually here there is actually a queue. Okay, there is actually a ready queue. Okay, so every time you emit a new task, okay, or you create a new task, it joins the ready queue. All right, so at any point in time, you can have multiple tasks all in the queue. All right, and what happens is one of them will be selected to transition to use the CPU. Okay, now when I transition from ready and I move over to using the CPU, that means I'm actually executing code. That is what I call being in the run state. Okay, the responsibility, okay, lies in this part of the OS or this manager called the scheduler. So the scheduler, you can think of him as the overall manager who decides who gets to transition from ready to run. Okay, who gets to transition from ready to run. So when I'm running, I'm using the CPU. When I'm ready, I'm not yet using a CPU. I'm in the queue waiting for my chance to run. So you can imagine I can have n number of tasks in the ready queue, and out of those n number of tasks, only one will be selected to run. Everybody else is still waiting in the queue. All right, so everybody else is waiting in the queue. Now, when I'm running, two things can happen. One is I may run till I hit a timeout. What is a timeout situation? Timeout means the OS is trying to do some sort of a round robin. That means I allocate you some CPU time, okay, to use the CPU for 5 milliseconds. The 5 milliseconds is up, now you transition out. All right, so when you transition out, you'll go back to the ready state. All right, but at the same time, all right, okay, so let's say now you transition out to the ready state, then your scheduler will now have to select somebody else to go in, correct? Okay, somebody else to go in. Now who will go in? So this scheduler, the rules that govern the scheduler are basically the fundamental rules that determine how the OS behave. All right, so in RTX or most RTOS systems, when you say you have a real-time system, your scheduler must be what we call a preemptive scheduler. Preemptive scheduler based on priority. That means it will look at all the tasks that are in the ready queue and select the one with the highest priority to take over the CPU. All right, so that is how the scheduler works, okay, in our RTX RTOS. For most general purpose OS, okay, like your desktop OS and so on, they use a different type of scheduling policy known as cooperative. Okay, so cooperative scheduling policy means you have more or less a fixed time slice approach. Okay, so it's a round robin kind of a thing where you can transition between every task, all right, with giving a equal share to the different tasks in the system. All right, so in a RTOS concept, you have to have a scheduler that is preemptive in nature and where you have priority as the base deciding factor on who gets to run. So that's why I said earlier, priority is very, very important because that determines who is the most important or which task is the most important in the whole system. All right. Now, while I'm running, so we talked about this option. Now there's another option here, okay, where I can go to an event wait, okay, or what we usually call a block state. Okay, so what is a block state? Okay, so a block state means I'm running and I wanted to do something and I couldn't do it. Okay, I want to do something, I couldn't do it. So if I cannot do it, that means there is no point in me holding on to the CPU. Alright, okay. Why I couldn't do it could be several reasons. Alright, maybe I wanted to access a particular shared resource, okay, a array or a buffer, but then it's not available at the moment. Alright, so I wanted to do something, okay, and I cannot do it because that resource is not available at this time. So if the resource is not available at this time, there is no point in me holding on to the CPU. Alright, so I will go to a block state. Okay, so when I go to a block state, what am I implying? I'm implying that I am still waiting for some resource to be available. Alright, so I do not go and join the ready queue, because ready queue means I have all the resources I need to transition to run. Alright, so if I do not have something, then I'm not ready. I am blocked. That means I'm waiting for something. What is that something? It could be a shared memory, it could be a resource, it could be a peripheral block. Okay, maybe I wanted to do a to D operation, but all the A to D modules are used up by other tasks. So somebody must free up something. Correct? So I'm waiting. So as long as I do not have all the resources I need, I will transition to the block state. Only when that resource that I want is available, then I will transition to the ready state. How will I know that this resource is not available to me? Okay, so that is where you must use the proper OS structure to manage your resources. So which we will be learning, okay, throughout the next few labs. How do I make sure that I use the proper OS sort of constructs to manage resources, so that if I want a resource and I cannot get it, I will go to the block state, and when the resource is available, I will go to the ready state. If the resource is blocked while the task is in the ready queue, it doesn't matter, because you only need to worry about it, okay, when you transition to run. Okay, if you are in the ready state, okay, so what you're saying is there is a resource, correct, and you are already in the ready state, so the resource was available, but since some other task was running, that resource is now blocked, correct, and so what will happen? Okay, so what will happen is, since you are already in the ready queue, you will get a chance to run, and when the time comes when you try to access the resource, all right, and then you realize it is blocked, correct, it's not available, then you will transition to the block state. All right, so you will still get a chance to run only when your code tries to access that particular resource and realizes that it's not available, then you transition to the block state. All right, so it is all managed in the backend by the OS. So it's very important you understand how to use all these OS sort of frameworks correctly in the code. Okay, if you use the framework correctly, everything will run very nicely, right? Because everything is done by the OS for you. But you need to know how to make sure how to apply all these OS concepts correctly in the code. Okay, so the last one here is release. Okay, so if you look at the code here, so we're done running a block. The last one is exit. Okay, and exit, like I said, is not usually something we consider in our case, because we don't create a task if it's only a one-off thing. All right, so we create tasks with the idea that we want to do things with some level of repeatability. Okay, so these are the transition. Okay, so the process states, like I said, they are all recorded inside the process control block. So inside the process control block of each task, it actually keeps a record of everything, the state, the memory, what is happening, everything. Okay, so everything is managed inside the process state control block. Yes, if a process exits, that means the OS does not see it anymore. So you need to call the new OS thread new to restart and readmit it into the OS. Okay, it cannot run anymore. Okay, the moment a process exits, so as long as you never exit, so as long as I'm staying within here, all right. So okay, maybe I should not do that. Okay. Okay, so let me read all this. Okay, so basically this is the main 3 blocks here. Okay, in most cases, all right, your task will be within these 3 blocks: ready, running, block. The new to ready is just a automatic transition that happens by default that is managed by the OS. Okay, after that, you only expect to be within these 3 different states. The exit only comes if you really want to terminate, but if you terminate, you can never come back in until you call new again. Okay, and you re-admit it into the OS structure. Okay, so this is an example of the different states, all right, and the block states. Okay, so I'll not go into it now. All right, so we will look at it later. Okay, so now what I want to do is okay, how are we going to deal with OS in the code? All right, so what I'm going to do now is, if you open up your tutorial, okay, so I sent you all the tutorial 4 just now. Okay, so there are a few questions here. All right, so what I want you all to do is to discuss question 1 first, and how we're going to do this is I'm going to send you all to, how many people are there? Okay, about 50 people. I'm going to send you all to about 8 different breakout rooms, okay, randomly. So inside your breakout rooms, you all just have a discussion on question 1 first, and then we will come back in a few minutes to discuss your answers and suggestions. All right, so I'm going to send you all now first, and we'll come back in. All right. Okay, so sorry for ending your discussions. Okay, so let me share the screen and discuss a question. Okay, so let me share this first. Okay, so I hope you all had some fruitful discussion, okay, on the questions here. Okay, so if you look at the first question here, they ask us, task A is running and chooses to give up the CPU voluntarily. What state does it go to? So if I'm running, so currently this is task A, right? And I'm running. If I choose to give up the CPU voluntarily, what is the implication? I mean, what is the main understanding? That means, do I still have all the resources I need to carry on? Yes or no? Okay. Yes, correct. Because I am running and I choose to give up the CPU. Right. That means if I'm running means I have all the CPU resources. I mean I have all the resources I need, and I choose to voluntarily give up. Correct. Even though I have everything. So since I have everything and I choose to voluntarily give up, then I will go to the ready state over here. Okay, so it will transition to the ready state when it goes to when it decides to voluntarily give up the CPU. All right, so that is the first scenario over here. Now let's look at the next one. Task A is running and a higher priority task B becomes ready. So what happened? Okay, so right now I have task A that is running, and task B, which is higher priority, becomes ready. That will happen. Yes, so the other way, so the only other way, so I mean, to go transition from running to ready is usually 2 ways. Either you get timeout, okay, if your time slice is up, all right, or you can call a function, okay, or you can choose to voluntarily give up the CPU, okay, or we call yield the CPU, all right, then you also give up the CPU and then you transition to ready. Right, so these are 2 different ways in which you will transition from running to ready. Okay, so for this scenario here, if task A is running and task B, which is a higher priority, gets ready, what will happen? So the first thing we must understand is the scheduler that we are using, right? The scheduler is based on what? It's based on the preemptive mode of operation, where the main deciding factor is priority. That means the moment a higher priority task becomes ready, that should take over the CPU. Correct? That is the whole idea of RTOS based system. Correct? That means somebody or some other task is more important. So that task should be allocated CPU usage. All right. So that means that task B must automatically transition over and switch to the running state. So the running should now become task B. Okay, so that is the first thing you understand. The moment a higher priority task becomes ready, that means it must take over the CPU, because that is the job of the scheduler, to make sure the highest priority task takes over the CPU. Now the next thing is, where does task A go to after this? Okay, so task A, if it was running and task A did not try, it was not a scenario where task A tried to get something it couldn't get, correct? It is just the case where somebody more important came along. So since somebody more important came along, that person is going to use the CPU while task A transitions to the ready state. So task A will come here. All right, so there's a question for part A. Why does task A not exit for part question A just now? Okay, exit is only when you explicitly want to terminate the task. In this case, your task A is still running. Okay, your task A is still running. Okay, task A is still running, and then it gives up the CPU. If it decides to terminate, then it will go to exit. Okay, but in this case, I'm giving up the CPU. That means there could be other tasks waiting in the ready queue, and I choose to give up the CPU to allow other tasks to run. So in that case, I'll go to the ready state. If I want to terminate myself, then I go to the exit state. Okay, so there are two different things. Okay. Okay, if task A is still the highest priority, all right, and there are no other tasks that are higher than task A, then you will schedule back to run again immediately. All right. So I will go through one of the OS course later to explain how this thing might work. All right. But effectively, if you give up the CPU voluntarily and you are still the most important person, then effectively you are still running. All right. If there is somebody else with equal priority, then that person will get a chance. All right. That is how the schedule will behave. It looks at priority. Okay. So okay, is it possible for no program to be running state, but every program is a ready state? If every program is at ready state, then something is wrong with the program, correct? Okay, why? Because technically, if everybody is waiting for something, then when will anybody get a chance to run? All right, so technically, the way you design your architecture should be that somebody should always be running. All right, of course, in the OS itself, all right, even though the task that you write, you may not get any task running, the OS itself has an idle thread that will be running. Okay, which will be running in the background to just make sure the CPU is active, and it will take care of other activities that are in the backend processing. All right, but even if all of your tasks are in the running or not in the running state, okay, there will still be a task that is running. All right, if you have tasks in the ready state, okay, as long as you have any one task in the ready state, the scheduler will transition that to the run state. So it's not possible, all right, it is not possible for a task to be in the ready state and no task is running. Okay, it's not possible, because the moment you are in the ready state means you have everything that you need to run, and it's the responsibility of the scheduler to transition you to the run state. Okay, so it's not possible to be having all tasks ready and no tasks running. It is possible that you can have all tasks blocked. Okay, that is also a bad design. Okay, but it's possible to design a bad design in such a way that all the tasks get blocked and then no task is in the ready and no task is in the running. That is possible. Okay, but it is not possible to have tasks in the ready and no one running. All right, then something is wrong with the OS, because the OS job is to make sure that somebody is running, and who is running? The highest priority in the ready queue. Okay, so that is the job of the OS. So that's why I said the structure is important. You must understand how to create the structure so that everything is handled by the OS for us. Okay, so let's carry on first. So currently I have task B in the running state and task A in the ready state. Okay, and question asking that saying that task B requests for some resource and is unable to acquire it. Okay, it is unable to proceed without this resource. What happens? So if task B is now trying to acquire a resource, okay, so this term resource, we will use it quite interchangeably, all right, in the most material. So it's just a general term. It could refer to a shared memory, it could refer to a hardware block, subsystem, anything. All right, but you just take it such that when I say I'm requesting for a resource, means it is something I need. Correct? If I don't get it, I cannot carry on. Okay, so that is the basic understanding you must have. So in this case, if task B is requesting for a resource and I'm unable to get it, what will happen? Task B goes to which state? Yes, okay, so it will go to the block state. So always remember, when I'm in the running state, that means I'm using the CPU, and if along the way I try to get something and I cannot get it, I will transition to the block state. So task B will come to the block state. Then what will happen? Anything else? Is there anything else that will happen? All right. So the moment a task exits the running state, who will come in? Our manager will come in. Who's the manager? The scheduler. Okay. Every time there is going to be some transition, the scheduler will be invoked. He will come in. Okay. The scheduler will look at all the tasks in the ready queue. So like I said, you can have a lot of tasks in the ready queue. And it will select the task which is the highest priority. So if task A is the highest priority in the queue, then task A will get to transition over. If there's some other task that is higher priority, then that task will transition over. Okay, so the next task that is in the first in the queue, okay, for the ready queue, that task will then be scheduled to transition to the run state. All right, so that is what will happen. So two things will happen here. Task B goes to blocked, and task or the highest priority task in the ready queue will go to run. Okay. Okay. Now, so we have task B over here. Okay, so let's assume that there is no other task. So let's assume that task A is here. Okay, so after 5 milliseconds, okay, so the resource required by task B is available. Then what will happen? Okay, good. All right. So most of you are getting it. All right. So after task B, so task B will stay in the block state until the resource becomes available. All right. So when task B resource becomes available, what will happen is it will become unblocked, so it will transition to the ready state. Okay, so you must see that there is no arrow from block to running. Okay, there is no arrow from block to running. When I'm in the block state, the only next state I can go to is ready. All right, so from block state I will go to the ready state. All right, where I go over to the ready state, then what will happen is I will be able to I will then invoke the scheduler again. So the scheduler will look at the task B, which is now in the ready queue, and since task B is higher priority than task A, it will then transition task B to run. Okay, so task B will come here, and since task A was running at that time, all right, it will be transitioned back to the ready queue over here. So task A will come here. Okay, so a few things will happen. First, task B will be unblocked. So it will go from block state to the ready state. All right, and once I'm in the ready queue, the scheduler will see that a higher priority task is now in the ready queue. So it will transition task B to the running state, and task A, which was running, will now transition to the ready state. All right, so these are the sequence that, or this is the sequence that will happen, okay, in this scenario over here. Okay, so all right, so the operating system will constantly do some sort of polling to or monitoring to check, okay, whether the resource is available or not available, or it is been released and things like that. All right, so it is not interrupt based because it's fully software, correct? But you can imagine that it will run very fast in the background, so that the moment some event triggers some resource available, you can automatically transition states to their correct level. Okay, so it does this through its own sort of system tick. Okay, so OS has its own system tick that keeps track of all these background activities. So like I said, there are a lot of threads that will run in the background where the OS will monitor and keep track of everything is happening. All right, so as and when events happen, you will be able to quickly transition the different tasks to different states. All right, but all this is, so that's why the OS itself is very powerful, because it can run all of this backend processing for us while still delivering real-time response for the main application code that we are writing. Correct. So that is why OS itself requires a fairly good and a solid system to run on. All right. Running a OS requires a fair amount of system resources, right? CPU as well as memory. So the more powerful the overall system is, the more effective your OS is. All right. All right. So for the rest of the questions, all right, we will discuss during next lecture. But just I want to point to you the link just now that I sent over in the chat group. I'll send in an announcement as well. So this link is the online documentation for the RTOS that we are using. So all the RTOS calls that we are going to deal with, everything is actually explained here, all right, in detail. For the code that is given in the tutorial, you can refer to these sort of initial examples here. So we are just looking at a few different codes first. The OS thread new, okay, so that is to create a new thread, all right, and so some of the details and everything is explained here, all right. So you can look at this documentation first, all right, and you can relate it back to the sample code that we have, all right, and then you can try to see how to answer. I'll go through this in more detail in the next lecture after the recess week. Okay, so do we have a midterm? Yes, we do have a midterm. If you look at the schedule that I shared in the first week, it will be in let me see, week 9. Okay, so the midterm is scheduled to be in week 9. All right, and the topics will cover everything that we have done so far and the introduction to OS. That means this chapter as well. Okay, in this tutorial. Okay, so I will send out a detailed announcement on all the topics and all the things you need to cover. Okay, next week is recess week. Next week there's no class. Okay, the week after next week, that means in week 7, after you come back from recess week, that week you will not have any tutorial. I will do it as a tutorial in class, that means during the lecture itself. Okay, so this link is very important. Okay, please save this. All right, and it is a very good set of documentation. There are a lot of details which we will not go into, all right, because we're not going to very in-depth into the OS backend architecture at this point. We will be focusing more on understanding the various tools. Like I said, the OS is a very powerful tool, all right, but it's only as powerful as we know how to use it. All right, so we need to learn how to use the features of the OS so that we can effectively come up with a good architecture for our project. All right, so that is what we will be developing on over the next few weeks. All right, if you look at all the lessons and the labs, we are learning the different tools that OS offers us so that we can then decide how we want to frame up the architecture for the project. Okay, so as always, I occupy all my time. It's already 11 o'clock. Okay, sorry about that. So those of you who have questions, you can still stay back and ask. If not, thank you very much, and I'll see you all after the recess week.